All right, the last part of the chapter here is in 15.7. We're going to talk about Le Chatelier's principle, and this is actually a really easy principle, so hopefully this section shouldn't be too bad. What it is that you can predict which way an equilibrium will shift if you disturb it. All right, if you change the system, it will shift to undo that change. So the first thing we're going to look at here is a change in concentration. And you have a change in concentration, okay? So if I add a component to the reaction will shift to lower the concentration. If a component is removed, the reaction will shift to increase the concentration. So for example, we have this picture here, okay? And we have initial equilibrium. We add a bunch more H2. That means I'm going to lose some more H2, gain some more NH3, lose some more H2, and now I have equilibrium reestablished. Now this is with pressures, okay, but this is with the same reaction of the N2 plus H2 yields NH3 that we looked at before. So obviously H2, I added it, so I'm using it up. And then I reestablish now where my partial pressure or my concentration is now the same again. So for the reaction we looked at here, that I just mentioned again, okay, N2 plus H2 yields NH3. If I add N2 to it, that means that my N2 and my H2 are going to collide together, make more products. You make more products and the reverse reaction happens, and it goes back and forth until you again reach equilibrium. So we're going to go back and forth, undoing the change that you just added. So let's look at the example here. I'm going to predict the direction of the shift of the equilibrium position in response to each of the following changes in condition. And the first one you have is the addition of carbon monoxide. So if I'm adding more carbon monoxide here, that means I want to undo that change, which means I'm going to shift to the left. I'm going to make more reactants to undo what I just did. B, if you add or remove carbon or tetraarsenic hexoxide, which would be these two, well, what we notice about those two is those are actually solids. Solids have nothing to do with equilibrium, so those actually are going to have no effect on which way this goes. It needs to be a liquid, a gas, or aqueous. Okay, now if I remove some arsenic, remove some of this, then it's going to shift this way to get more of that I just lost. So it's going to shift to the right. All right, effect on a change in pressure. There are three ways to change the pressure of a reaction system involving gases. You can add or remove gases, reactant or product. That's what we talked about. We can add an inert gas, which is the one not involved in the reaction, or we can change the volume of the container. So if you add more again, it's going to shift to undo that change. Okay, if you add an inert gas, no effect on equilibrium. It increases the total pressure, but no effect on partial pressures of reactants or products. Now, if you mess with the volume, okay, if I have my volume reduced, that means that this is also proportional to the number of moles present. We talked about a long time ago that if I'm looking at a reaction, if I have this many liters of something, that is very proportional to that many moles of something. If we're talking about the coefficients out in front as to how much can react with each thing, okay? So the volume can be reduced by reducing the number of molecules. And the opposite, if my volume is increased, okay, your system will shift to increase the total number of gas molecules. They kind of take up more space, so I have more particles. If I have more particles, I have more pressure. Because when you're increasing the volume, now I'm lowering the pressure. So in order to undo that pressure that I'm lowering, I have to then add more gas molecules to get my pressure to go back up to what it once was. So let's look at an example. Predict the shift in equilibrium that will occur for each of the following processes if my volume is reduced. So if I am making my volume go down, you need to look at the number of molecules that you have. And by doing that, we look at the number of coefficients that we have. Okay, so look at A. We don't count solids, only gases or solutions. I don't count liquids. So in A here, you're going from 6 molecules to 0 molecules. So I want to get my volume to go, if my volume is reduced, that's going to build my pressure up. I don't want to build my pressure up, so I need to get the number of molecules to go way down, which means I need to shift towards the 0, and I need to shift to the right. Okay, let's look at the next one. All right, they're all gases, so we're good there. We're going from 2 to 1. Again, my volume is going down and my amount to go down. So again, we're shifting to the right. If you look at the last one, I have phosphorus trichloride and ammonia. We look at how much we have here. I've got 4 here. I've got 4 on the right. So we're going to have no effect by changing or the volume any. The effect of a change in temperature and how that varies your K. That is the only time that a constant is going to be varied. Remember, look at that equation where we had that for converting between a K and a Kp, there was temperature in it. Well, the same thing goes with this, okay? If you have a change in energy, which is a change in temperature. So if energy is added by heating a reaction, it will shift to consume that energy, which is the same thing we were just saying about pressure and volume and concentration, okay? So if I have, for example, this lovely N2H2 stuff that we've been looking at, okay? And I have a little chart that's going to show my how this works. All right. So if I have N2 plus 3H2 yields 2NH3, they have to tell you one thing. They have to tell you where is my heat here, and they have to tell you that my delta H for this reaction is negative 92.38 kilojoules. And all I really care about is the fact that this is negative. If that is negative, that means my reaction is exothermic. If it's exothermic, that means heat is considered a product. Okay. So if I add more heat or more energy to this system, this is going to shift to the left to get rid of that heat that I have. So if I'm shifting to the left, that means my concentration of NH3 is going to go down, and my concentrations for N2 and H2 are going to go up. Well, if my products go down, my reactants go up, my value of K is going to go down. That's what we see. Okay, my temperature goes up, I'm adding more heat, my K values go way down, 10 to the negative third, 10 to the negative sixth. Think of energy as whether a product or a reactant, and they have to tell you what that is based on whether it's positive or negative. So for example, we're going to predict how the value of K will change as my temperature is increased. So I'm positive here, which means that my energy as a reactant is positive. So my heat is over here. My heat is over there. I'm going to increase my temperature. So if I add more heat, it's going to have to shift to the right to get rid of that. So it's going to shift to the right. Okay, that means that I'm going to have more products. If I have more products over reactants, now my value of K is going to start to go up. Okay? Now look at this next one. It's negative. It's the same way. It's exothermic. So the same way as the very first example we looked at, which means it's going to shift to the left. As it shifts to the left, that means I'm going to have less products. I have less products. My K value is going to start to go down.